Hello everyone and welcome to this video. Today we're gonna cover operations research. As you can see, we're gonna discuss some definitions, we're gonna define operation research, and we're gonna go through some examples and some other stuff related to operations research. And so what is operations research? Operations research is the scientific approach to execute decision making. It is the art of mathematical modeling. So it is mathematical modeling. Operation research basically modeling mathematically, which is a mathematical modeling of complex situations. So it's also the science of the development of solution techniques used to solve these models. And it's also the ability to effectively communicate the results to the decision maker. So these are all different definitions to operations research. And we're gonna go through some examples of where can be this when can this be applied. So basically, when we have any complex problem of optimizing, say, sales or minimizing costs, maximizing the output, we're gonna need to have a mathematical model for that. Yes, it's gonna be real life, but we're gonna need to model it. So we need to have some numbers backing up our work. And so also we say the science of development of solution techniques. So we need to develop solution techniques, and we'll be able to also effectively communicate the results to the decision makers. And so what is operations research? So it's basically, it has its early roots in the World War II, and it's flourishing in business and industry with the aid of the computer. And its primary applications and applications area of operation research include production planning, scheduling, inventory control, location problem, capital budgeting, and transportation. So it's involved in many areas of operations research. And so there are different operation research models. So there is the deterministic models, which assume that all data are known with certainty. So these are called deterministic models. And there are also stochastic models. So they explicitly represent uncertain data. So it involves uncertainty via random variables or stochastic processes. So yeah. So there are some differences. So deterministic models are use linear programming or network optimization, integer programming, nonlinear programming, inventory models, and stochastic models. Hope I'm pronouncing that right. So it depends on discrete time Markov chains. So these are different ways of doing these models. So continuous time Markov chains, queuing theory, so waiting lists or waiting lines, and decision analysis, inventory models, and simulation. So these are the different models and the different ways we can use these models. And so there is also problem solving and decision making. So, and there are 7 steps of problem solving. And yeah, so the 7 steps of problem solving, the first 5 are basically the process of decision making. So these are the process of decision making, and then the rest are part of all the problem solving steps. So let's walk through them. So identify and define the problem. So that's our first step. We need to identify and define the problem and state it clearly in order to be able to solve that problem. Then we need to determine the set of alternative solutions that we have, and then determine the criteria for evaluating the alternatives, and then evaluating the alternatives and choosing an alternative. And so then we need to implement the chosen alternative after we evaluate alternatives, determine the criteria, determine the set of alternatives. We need then to implement the chosen alternative and also to evaluate the results of the alternative. And so these are the 7 steps of problem solving. Now let's go through the mathematical models. So mathematical models basically relate decision variables, which are the controllable inputs, with fixed or variable parameters, which are uncontrollable inputs. And so it relates the controllable inputs with the uncontrollable inputs. So they frequently seek to maximize or minimize some objective function subject to constraints. Yeah, so these are the mathematical models and are said to be stochastic if any of the uncontrollable inputs or parameters is subject to variation or random, otherwise are said to be deterministic. Okay, so it's said to be stochastic if any of the uncontrollable inputs are variant. So if the uncontrollable inputs are variant, then we're gonna say it's stochastic. Otherwise, if they are not variant, then we're gonna say it's deterministic, and that involves uncertainty and certainty in our models. So generally, stochastic models are more difficult to analyze. So since they involve randomness and uncertainty, and that's why we see they're gonna be more difficult to analyze. And the values of the decision variables that provide the mathematically best output are referred to as the optimal solution for the model. Optimal solution for the models. So the values that that optimizes our output is basically the optimal solution. So you can understand the difference between stochastic and deterministic models. And so let's go through an example. So our example here is on Ironworks Incorporation. So I know Ironworks manufactures two products made from steel. So it manufactures steel and just received this month's allocation of B pounds of steel. Okay, so that's the number of pounds they have of steel. And it takes A1 pounds, okay, of steel to make a unit of product one. So let's say it takes 1 pound to make a table, to make a chair, okay, or to make a specific kitchen equipment, so made of steel. So it takes A1 pounds. We need to make this chair A1 pounds. So we need, say, 50 pounds. And then and it takes A2 pounds to make a unit of product 2. So let's say product 2 is just, you know, like a cup or a bottle, so steel bottle, something like this, and it takes 10 pounds, okay? So, and basically, they are producing these two products, product 1 and 2, and these are the rates or the pounds that we will need for each product. So, and let x1 and x2 denote this month's production. So, x1 and x2 just basically the number of units produced, okay, per month, respectively. And we also need to denoted by P1, P2, the unit profits for products 1 and 2 respectively. The manufacturer has a contract calling for at least M units of product 1 this month. Okay, so they want at least M units of product 1. So let's say X1 should be less than or bigger than or equal to M, which is at least. Okay, and we know that X1 is the number of products we have this month and M is our minimum. And so also the firm's facilities are such that most U units of product 2 may be produced monthly. So we want to maximize U, the number of units produced for U for product 2. And so that's basically, let's see here. Yeah, so that's the same problem. Okay. And now let's go here to the mathematical model for product here or for this company. So the mathematical model is the total monthly profit. So if we want to find the total monthly profit, how can we do that? So basically profit is gonna equal to the profit of x1 or product 1, let's say product 1, multiplied by the amount of product 1 produced. Okay, so this is product 1. Now talking about product 2, so the profit of product 2 just basically gonna be the profit times the quantity, let's say, of product 2. And that's basically our total profit. So, and if we say that P1 is the profit for product 1 and P2 is the profit for product 2, then basically we can model this as P total equals P1 x1, x1 number of units for product 1, P2 x2, okay, and that's basically our mathematical model. And if you want to maximize this, maximize profit, so we're gonna say max P1 x1 plus P2 x2, and this will maximize our profits, as you can see. And now maybe we have, yeah, so let's say we have some constraints on the amount of steel that we have. So we don't have infinite, we cannot produce infinite number of steel, because if we want to maximize this we would say infinity, so we produce infinite numbers of x1 and x2 to maximize profit. But basically we don't have infinite resources nor infinite materials or labor or time or etc. or machines. So, and that's not possible. That's why we need to also we need to be able to work within constraints. So we'll have constraints. So the total amount of steel used during monthly production is just the amount of steel required per unit. So let's say the amount of steel we need per unit is A1 X1, okay, and let's say it's A1, then multiplied by the monthly production of product 1. And we said the monthly production of product 1 is X1, and we add A2 plus A2 X2, okay, multiply it, and this is the amount of steel needed, and this is the number of steel for product 2. And this quantity must be less than or equal to the allocated B pounds. So A1 X1 plus A2 X2 should be less than or equal to B. And that basically says that we cannot, the amount of product here that you can use cannot be lower than the amount we have in the inventory, which is B. And that's basically a constraint. So we call this constraint. And we usually operate within constraints because in our life we are constrained by many things, and that's why we need to make sure we take those into account. So we have our example, Ironworks Incorporation. So we have our mathematical model. So the monthly production level of product 1 must be greater than or equal to M. So we have another constraint. So we cannot have X1 less than M. We want it at least to be M. Maybe we have contracts with other companies and we have some requirements that we need to meet, and that's why we just need to have it bigger than M. And we also may have the monthly production level of product 2 must be also less than or equal to U. So maybe we cannot exceed a number of production for product X2, maybe because we do not have, or we do not need that number, since we do not have a lot of contracts maybe for this. And so however the production level for product 2 also cannot be negative, okay, so nor x1 can be negative, okay, but since we say x1 is bigger than m, so this is included in this, so this is included in this, and yeah, so x2 cannot also be negative, we cannot have negative products, so x1 x2 bigger than or equal 0, it can be 0 but cannot be negative. And so now we have our mathematical model that we have made. So we want to maximize the profit, but we also need to make sure that such that A1 x1 plus A2 x2 is less than or equal to B, and that x1 is bigger than or equal to M, and x2 is smaller than or equal to U, and also x2 is bigger than or equal to 0. Okay, that's our mathematical model summary. So these are all the constraints, and this could be modeled by a computer in order to maximize the profit. So now we have a question with numbers, and I think this is something we need to go through. So now, let's say, suppose we have 2,000 of steel, let's say 2,000 kilos, okay, so kilos. And then we need to produce, so to produce product one, we need 2 kilos. To produce product two, we need 3 kilos, okay. And then M is just the minimum number of product one, so minimum x1, and it's basically the maximum. Is it the maximum? Yeah, the maximum of product 2, so max x2, we cannot exceed this number of product 2. And P1 is just the profit for product 1, and P2 is the profit for product 2. And we need to write this model for these specific values of the uncontrolled inputs. And basically, we can just plug in the numbers from the model that we have. So P1, x1 plus P2, x2. And we have P1 is just 100, x1 is just the value that we want to find. We have x2, and we need to make sure that our constraints are also met. So the rate for product 1 is 2 multiplied by x1 is 2x1, and we have the product or the rate for x2 is just 3, so 3x2 is less than or equal to 2000, and we want x1 to be bigger than or equal to 60, x2 smaller than or equal to 720. These are all the constraints, and we want so maximum. The max number of product 2 is 720, and the minimum number of x1 is just 60, and x2 cannot be negative, of course, and that's basically what we need to evaluate. And so now the optimal solution to the current model is x1 equal to 60, and x2 equals 6 to 6 and 2 over 3 products. So, and if the products were engines, for example, so we need to explain why this is not true optimal solution for real life problem. Yeah, so if we say that the optimal solution is x equals 60, so we need to produce 60 units of product 1 and 626 units and 2 over 3 of product 2, and this is the optimal solution. Would say that this, okay, so he's wanting us to explain why is this not a true optimal solution for the real life problem. And I think if this is an engine, it will be not optimal to produce 626 products, since we may not, yes, this might maximize profit, but we might not also have the demand for these engines. Maybe we just have demand for 60 engines, and for product 2 100 engines. So we need also to take into consideration the demand and supply and demand. That's important. So, and also, yeah, okay, so he's talking about also 2 over 3. Okay, so it's not actually the number, it's about the amount, it's about the number itself. It cannot be a fraction, so we need to produce 626 to optimize this, basically. So we cannot produce until 2/3 of an engine. Those the problem is further restricted by the fact that both x1 and x2 must be integers. So we have a constraint also, x1, x2 are part of n, is it? Like they are integers, are integers, so this is also another constraint. And so they could remain fractions if it's assumed these fractions are work in progress or to be completed the next month. That's also a consideration. So yeah, so we can take 2 over 3, assume that it's gonna be work in progress, and it's gonna be made later on, or yeah, so made the next month. And so there are some application areas. So these include strategic planning, supply chain management, pricing and revenue management, logistics and site location, healthcare management, optimization. So these are all applications of research operation, and mainly the main problem or the main issue an industrial engineer that's going to deal with. And so we have optimization, marketing, research, scheduling, portfolio management, inventory analysis, forecasting, sales analysis, actioning, and risk analysis. All of these are basically application areas. And so these are some examples we can go through. Okay. Okay, I think we're gonna stop here and we're gonna continue later. Thank you for watching. I hope this was helpful.